Hi everybody. Sorry I have to be gone again today. So I think you all know what's going on. I'm really hoping that um, I'll be back on Thursday, but have to remain a little flexible. I definitely look forward to seeing y'all. So today, this is not going to be very long. Going to just a little review. Going to look at a problem that involves an object sliding down a ramp, an inclined plane, where there is some friction. Going to look at a slide to a stop problem. This is a problem type of problem you'll see on the test. And want to look a little bit again at Atwood's machines with friction. Make sure that you are working on your practice problems. There are 3 sets of them. When we're done with this, please make good use of your time and make your way through some of this stuff. Just a reminder that we are wrapping up Unit 6 on Wednesday the 13th. And then after that, we'll be looking at work, energy, and power. And one of the things I really like to talk about in the course of the year are simple machines. Changing the calendar a little bit for Unit 6 from what was originally planned. So originally, the quiz was supposed to be Friday. I'm moving it to Monday. And I was hoping to have this Atwood's machine with friction lab today or tomorrow, but I am just really going with the goal of being back on Thursday. So we'll do that lab Thursday or Friday when I can be there, unless something really funny happens around here. And funny would mean not very funny. So we're going to go with not funny for once. Wait a second, you're never funny, Mr. Drawing Aid. Shh, keep it to yourself. All right, let's look at this first type of problem. Inclined planes, objects with some friction. All right, so we have a 4-kilogram brick. It's on a very steep incline. 62 degrees is very steep. We have measured that the coefficient of friction between the brick and the surface of that plane is 0.456. So your goal is to calculate the acceleration of the brick down the plane. I want to give you a couple minutes to give this a try. So please pause the video now and give this a try. Definitely discuss with each other. So please pause now. And we're back. So if you got it, great. If you're still looking at what to do, we're going to walk through it and just follow along. So these are the steps you need to go through. You need to find the force that's parallel to the surface, so the amount of the brick's weight that is trying to drag it down that ramp, that inclined plane. You need to figure out how big the force of friction is going to be. The unbalanced force is going to be the difference between those two. One force is trying to drag it down the ramp. One force is trying to resist it. That will give us unbalanced force. Unbalanced force is the amount of force that we actually get to use to accelerate an object. Then we go back to Newton's second law, fun is mom. Here is what we're looking at. So parallel force, there we go. We know the mass. We're on Earth when we're just going absolute values for gravity, 9.8. Sine 62, make sure your calculator's in degrees. So we get that as the amount of the brick's weight that's trying to drag it down the surface. Friction. We have that coefficient of friction, that 0.456. We know the mass, 4 kilograms. Once again, we are on Earth. We know the acceleration of gravity. And we have cosine of the angle. So that term that involves the 4 kilograms times gravity times cosine, that's what we call the normal force. That tells us how much the brick and the surface are being pushed against each other. And that works out to a little bit over 8 newtons. So 34.61 newtons trying to make it move, 8.39 getting in the way for an unbalanced force of, drum roll please, almost 26.25 newtons, 26.22. Okay, last things last. Fun is ma, but we're trying to solve for acceleration, so it's got to look like that. And turns out to be that. I think in the original, it says 6.55 up at the top. This is 6.56. So minor rounding differences is the only reason that is. Okay. Want to move on now to a sliding to a stop problem. So it's another brick. It's a little smaller, 3 kilograms. And you give it a good horizontal chuck. And it starts to slide across the frozen pond. At the moment that it makes contact with the pond, it is traveling quite fast, 26 meters per second. That's getting close to 60 miles an hour. So you got a good arm. And the brick slides a better part of a football field, 83 meters before it finally stops. The question is, what's the coefficient of friction between the brick and the surface of the pond? So once again, please pause this for a couple of minutes and please discuss, give this a try. So please pause now. And we are back. So this is a case where friction is the unbalanced force. An unbalanced force is whatever causes an acceleration. In this case, it's an acceleration that's making the brick slow down. But you have let go of the brick, so you are no longer pushing against it. Only thing that is changing the speed of the brick is friction. So again, friction is the unbalanced force in a slide to a stop problem. So here are the steps you need to take. You need to first figure out the acceleration. We have done this before. It's kinematics. Need to figure out the unbalanced force. Okay. Well, once we have acceleration, that's no problem because we have the mass. Got to figure out the normal force. Not hard. We have a mass, we know what planet we're on, and we're going to assume that a pond freezes horizontally, so that angle is going to be 0. And then we'll know the force of friction, because the force of friction is the unbalanced force. That's what you will solve for in part B. We'll know the normal force, and we can solve for mu. The famous cow-cat call. So here's what you get for the steps. This is what we would do to find them. So that first one, that's that kinematics. We know the final velocity is 0. It stops. We know the initial velocity. That's that 26 meters per second. We're solving for acceleration and the distance it slides. Here I'm using d as just a generic distance. You could very easily write x. That would be very correct. But the distance it slides was that 83 meters. Fun is ma. So once we have that 4.07 meters per second, we just multiply it by the mass of the brick. Normal force. Again, we got the mass of the brick right there, 3 kilograms. Gravity, 9.8. Cosine of the angle is 0 degrees. Horizontal is 0 degrees. And cosine of 0 is 1. Then finally, we're solving for mu. Force of friction, again, is the unbalanced force. So when we see that equation, F with a little F down there, that's force of friction. That is that 12.22 newtons. We're solving for mu, and the normal force is that 29.4 newtons. So you should get familiar with a sliding to a stop problem. Okay, last thing is to take a look at Atwood's machines with friction. And we looked at this before. We started off talking about an Atwood's machine without friction, just as a refresher. So what we needed to do is use this formula we've used before. Unbalanced force is m1g sine angle 1 minus m2g sine angle 2. And we're going to get fancy and we're going to say, oh yeah, friction will take away from the unbalanced force. Well, there just isn't any. So that force of friction is going to be 0. And we're calling the red block, the 12 kilogram block, the mass on top of the table, we're calling that mass 2. Horizontal is 0 degrees. So that term that says m2g sine angle 2, that's going to turn into 0 because sine of 0 is 0. And that first term, m1g sine of the angle, sine of 90 is 1. So it's in this system, no friction. The other block on top of the table, that's going to be accelerated by just the weight of the hanging object, that dark blue 4 kilogram object. And so we go back to using Newton's second law, fun is ma, to solve for acceleration. And again, all the mass moves because it's connected. Not just the 4 kilogram mass, not just the 12, it's all of it. We add 4 to 12, and we get 16. And I don't know why I'm talking this way. This is something you saw before about what you should write down. So this works for every Atwood's machine, no matter angles, whatever, where there is friction. We had this diagram just to remind ourselves of which force is which. Now you could call the mass on top of the table M1 and the hanging one M2. I happen to be calling it the opposite here. It really would not make a difference. Well, we just looked at this last problem. The red arrow, M2g sine of the second angle. Well, that angle is 0, and sine of 0 is 0. So that whole big red arrow is going to be a big fat nothing. Well, that means the dark blue block is going to fall downward, which is going to drag the red block to the right. That means friction will be to the left, because friction opposes motion. So this is just really a minor variation on the problem you just saw. So we go back and we use this. And we just put in the angles. And there's our formula for that. This is what the formula would turn into for this system. I wouldn't bother trying to memorize it for this system, just that top equation. It solves everything. Just remember what is 90 degrees, what is 0, angles, and everything in between. Speaking of angles, this we would solve like this if there was no friction. But if there's friction, that red term, that is the force of friction. Mu times the normal force between the red block and the table. So mu times m2 g cosine of angle 2. So that's your term for friction. Now, if m1, if the blue arrow ended up being bigger than the red arrow, that would mean that the dark blue block would go downwards and the red block would get dragged up the surface. And if it's getting dragged up the surface, friction would oppose the motion, and it would be in that direction. But that's only if the blue arrow is bigger than the red arrow. However, if the red arrow is bigger than the blue arrow, then the red block is sliding down the ramp. The dark blue block is being dragged upward. Well, if the block is sliding down the ramp, then friction would be acting in the opposite direction. Okay, I've got one more problem to quick walk you through, and then we are done. And then you should make good use of your time to get some things done. That does help me, so I would appreciate it if you could do that. All right, we got this two-block system. We've been looking at these just right this moment. So please, in a moment, hit pause, take a couple moments, discuss with each other, give this problem a try. And just to be clear, the red block I'm calling M1 in this case, because I'm eventually going to go through a solution, and I'm going to call the dark blue block M2. Again, just because I am choosing to do that when I eventually show you the solution. So please pause this now and give it a try. Pausing, pausing, pausing. And hello, welcome back to myself. All right, well, I guess welcoming yourself back is a little bit odd, but I'm doing it anyway. So here it is. This is just the generic formula that works for all Atwood's machines. Even ones without friction, it would just be that that term that says force of friction would turn into 0. Works for everything. So again, I happen to be calling the red block M1 and the dark blue block M2. So that's how I get this. Dark blue block is hanging at a 90-degree angle, straight up and down. And the red block is free to move across a 0-degree angle. So it would end up looking like that. Well, we know all this stuff. We know the mass of M2. We know the mass of M1. You're given mu, that coefficient of friction between the red block and the table. That coefficient of friction is 0.5. No measurement units on mu. G, well, we know G. And then we look at the cosine of the angle for the red block. Well, that is on a surface that is at 0 degrees. Now, sine of 0 is 0, but cosine of 0 is not 0. In fact, it's 1. So if we go through M2 times G, so that would be 60.2 kilograms times G, and then minus mu M1G, that would be 0.5 times 100 times 9.8, and this is what we get. So the hanging block, the dark blue block, exerts a force of 590 newtons trying to move this system, and there are 490 newtons of friction. So we only have 100 newtons to play with to make this whole system accelerate. Fun as ma. It's not just moving the red block, it's not just moving the blue block, it's moving all of it. And that's what we got. Okay, please make good use of your time. I really hope to see you soon, and I hope the rest of your day is good. Bye-bye.